Good morning, everybody, and I hope everyone can hear me. And very welcome to this next webinar presented by Spirax-Sarco. Today's session will be presented by the Gauteng Regional Sales Manager, Mr. Andre van Niekerk. Andre has been serving this industry at Spirax-Sarco for more than 20 years and is extremely well versed in everything steam. Myself, Cornelius, the National Sales Manager, will facilitate and post some questions. And we both are obviously supported very much by our marketing administrator, Debbie Robertson. Debbie, thank you so much. So for today, we will be covering a basic but very important topic of the steam and condensate loop, namely basic design, installation, and commissioning of steam systems. Often people ask why this is important, what impact it has on a system, and we hope to answer those and many other critical considerations in today's session. Having a mechanically correct steam system could play a big part in reaching our process productivity as well as sustainability objectives, with the added benefit of also reducing maintenance costs over time. And we won't be able to learn everything that there is to know in an hour session, unfortunately, but hopefully after today we'll at least be able to identify and start conversations around steam engineering best practice and proper mechanically correct steam engineering design. So as always, after the session, anyone on the call is more than welcome to contact myself or Andre or even your local Spirax-Sarco sales engineer to discuss any details that might have caught your eye in the session. And please feel free to reach out to us at any time to discuss these or any other steam-related topics. All right, before we get started, just some practical points very briefly. This meeting will be recorded and sent to everyone afterwards, so you can have some time later if you want to review something, you will have access to the recording for some time. The questions will be seen by the hosts only, which is us, and we'll post the most important ones into the chat as we carry on, and then we will address these at a later stage. We may not get to all the questions, unfortunately, and we'll reach out afterwards to make sure that we've answered as many of the questions as we possibly can. The way to submit a question, as you can see on the screen, you type the question out in the little box, you hit the send button, and that would post it on our side. We would then publish the questions and hopefully get to answer them. Questions would be answered at the end of the event, and as I said, the ones that we don't get to, we will make a plan to try and reach out after the webinar. So thank you very much for your attendance and your time invested with Spirax-Sarco today. Andre, over to you.
Great stuff. Thank you very much, Cornelius, and good morning, ladies and gentlemen. Thank you very much for attending this webinar with regards to basic system designs and consideration. So we have quite a few things that we want to cover in this hour, and as Cornelius rightfully said, unfortunately, we're not going to make you an expert in this subject, but we would like to highlight a couple of things that you can take with you when you walk onto a plant, or having a look at new designs and installations, which could definitely help you. And from there, if you have any further questions, you can feel free to contact Spirax-Sarco for that. So the agenda today, we are going to have a look at the properties of steam, just to understand the formation of steam and the various different energies that you find within it. We're also going to have a quick look at your boiler house with regards to feed tanks, boiler control, heat recovery, and some metering and monitoring system. We will spend some time in the distribution system, understanding the pressures, pipe sizing, and also some general design points, as well as your safety aspect of it, and also the insulation, expansion, and support. Then we're going to have a look at some process applications in steam conditioning and the grade of steam. We will be looking at pressure reduction and safety, some control loops, metering, installation configuration again, and one or two typical process applications, just to give you some examples. And then finally, we're going to get into condensate management, which is trapping and pumping, more in the pumping side. Have a look at some stall conditions and a little bit of flash energy recovery. So it's going to definitely be a fast-paced overview of this typical steam system. So I hope you guys stay with me. Right, so steam delivering advantage to industries. You can see that, almost all the items that you encounter day to day has gone through a steam system in its manufacturing life. The coffee you guys drank this morning, whether it be Recoffee, Nescafe, Jacobs, all of that, somewhere through its life process, it went through a steam system. The cold drink you might drink this afternoon when you have lunch, that definitely has gone through a steam system. The snack you might eat in the chips or the cookies, you know, somewhere in its lifetime it has touched steam. So steam is a very versatile heating medium, and therefore it has been used in most of the things that you have seen or touched during your lifespan. So when we have a look at the properties and advantages of steam, you know, steam needs to be considered totally different to other sources of energy, such as hot water or oil, because basically steam is a gas, and as such has different properties. And this brings a certain advantage, which we will cover as we go through this whole presentation. So when we have a look at the properties of steam, you know, it's a compressible gas, and we're going to have a look at that in the steam tables. It's very nicely, it's got a direct pressure temperature relationship, which is very beneficial to that of steam, as you can see at the advantages. You know, steam has a much higher heat content than that of water, and you know, it is very relatively light in weight when we come to the steam lines. It doesn't need to be pushed because steam flows with a pressure drop, and therefore you don't need any circulating pumps, and also you don't need any need for a balancing lines. So when we have a look at steam tables, we can see that steam is produced at various pressures. We call those gauge pressures, and at those pressures we have different temperatures. Each and every kilogram of steam at that various pressure and temperature will have three different entities of energies. We call them enthalpy of water, which is in the olden days known as sensible heat, as well as the enthalpy of evaporation, which is your latent energy, and those two combined will give you a total energy, which is your total energy of steam. But also this 1 kilogram of steam at those various pressure, temperature, and energy values will have a very crucial volume, which is made up when we talk about distributing steam. On the right-hand side, this is what we call the steam phase diagram. And to give you a quick crash course with regards to steam formation, we can see that water needs a certain amount of energy to be raised from 0 to whatever temperature it is required. In this example, they're making use of atmospheric pressure, which is your 0 bar gauge, which has a temperature value of 100 degrees Celsius. So to raise your water from 0 to 100 degrees Celsius, we're going to require 419 kilojoules per kilogram. At this stage, if we've entered all this energy, we have boiling water. Now we need a different energy to change that state from a liquid into a gas, which is called your enthalpy of evaporation. And that energy changes this phase now from a liquid to a gas without the temperature change. And once we have now applied the 2,257 kilojoules per kilogram at atmospheric pressure, we will have a dry saturated steam of 2,676 kilojoules per kilogram of steam at 0 degrees Celsius. But very important, as I said, that kilogram at that pressure will have a certain volume, and that is 1.63 meters cubed per kilogram. And as you can see from the steam tables, so it varies. As you increase in pressure, your temperature will increase, your enthalpy of water will increase, my apologies, and your enthalpy of evaporation will decrease, but your total energy will also increase. And because steam is a compressible unit, you can see that as the pressure increases, we will have a more compressed volume. If you can have a look at atmospheric pressure 0 bar, it's 1.673 meters cubed. And there we can see at 10 bar, it's sitting at 0.177. So all these factors have to be taken into consideration when we are designing a steam system. So as we just saw, from our pressure versus our specific volume, we know that each pressure has a different volume. So there we can see if a steam formation is a 10 bar gauge, we will have a volume of 0.1773 meters cubed per kilogram. But once we reduce that pressure down to 2 bar, we can see that this volume now changed dramatically to 0.603 meters cubed per kilogram. But what we also know that is when steam gives up its latent heat, we are left with condensate containing sensible heat. At the same time, the temperature and the pressure is that of steam. So when the condensate falls in pressure as it passes across the steam trap, there will be a sudden fall in pressure, resulting in the excess energy being converted from sensible heat back into total heat and causing a rapid expansion and a change of state back to what we call flash steam. That is what we will see from the video as you see now. And this is frequently vented to atmosphere, so not to cause any issues within the condensate network, which means that you have a loss of energy. And those are the type of things that we need to recover, which we will have a look at during this presentation. So just to review some key points, we also know that there is a direct temperature pressure relationship with both steam and condensate, as we said. When steam condenses, it gives up its latent heat or enthalpy of evaporation, but not its temperature. So we can see that if we now know the steam pressure, then we know the steam temperature. There we just said it a bit earlier, 10 bar, we now know that we have 184 degrees Celsius. But a steam heat exchanger or a plate heat exchanger operating at 2 bar will have the temperature of 132 degrees Celsius, as well as condensate at 132 degrees Celsius. So therefore, we know that whenever we get a fall in condensate pressure, we again get a release of energy in the form of flash steam, very similar to what we just showed you in the previous slide. Having a look at the boiler house, our energy center where steam is generated. Now, some consultants will never get involved with how steam is generated, but it is important to have a good understanding, as a failure to do so can have an impact with ongoing safety, maintenance, and absolutely process issues. The boiler house. The main components in this boiler house is definitely the boiler itself, the hot well or feed tank, and the blowdown vessel. Solutions typically supplied by Spirax-Sarco are showed in the blue. So units 1 to 32 is what Spirax-Sarco will provide. And whilst we don't make boilers ourselves, you can see that supplying the components that ensure the safety, efficiency, and reliability control and distribution of steam is our importance. So let's quickly have a look at the hot well, also known as the feed tank. This blends the condensate being returned to the energy center with any makeup water, where it is chemically treated and then held until there is a demand from the boiler. It is vented to atmosphere, and therefore the highest we can hold temperature is about 85 degrees Celsius, as we cannot risk a higher temperature being drawn through the feed pump, as this would cause cavitation. Many a times we have said that we would want this hot well to be as high temperature as possible, and that is true. But again, you have to take in consideration what temperature the feed pump can handle. Otherwise, you will definitely cause cavitation through the pump. A high feed water temperature has three benefits. First and foremost, is less energy being required to raise the steam than a lower temperature. We just saw that from the steam tables. At 419 kilojoules, we raised it from 0 to 100 degrees Celsius. And if we should go up to 10 bar, which is 185 degrees Celsius, we would require 781 kilojoules per kilogram. So if we can have a much higher temperature in our feed tank, it would mean that we would require less energy to get that water to its boiling point, therefore saving money. The boiler will respond more quickly whenever there is a demand for steam, because if we supply the boiler with cold water, what will happen is we will suppress the boiling rate, and therefore we will have a boiler that does not act on the demand if required. And thirdly, at a higher temperature, more of an entrained oxygen and non-condensable gases have been purged off, meaning that you will have lower costs of your chemical consumption. And as we know, or even you don't, the higher I can raise, or with every 6 degrees I raise my feed tank by returning condensate or recovering flash, every 6 degrees I raise that by means of doing that, I can save plus minus 1% of my fuel saving. More advanced boiler houses are now keeping their feed water under pressure of around 0.5 bar, which gives you approximately 105 degrees Celsius. The benefits that this brings is, first and foremost, it is pressurized, so therefore there is no venting, which means that the flash steam losses can be absolutely reduced. A higher temperature equals more responsive a boiler whenever there is a sudden demand, as what I've just explained. And also higher temperature equals less energy consumed to raise steam. So a higher temperature pressure means that we would require less oxygen and non-condensable gases that will be purged off. And this can be done without any need of chemicals. So that would be your saving, is to utilize less chemicals to get rid of oxygen, scavenging material, and those sort of things. When we also look at the boiler, we know that we need boiler level control. So modern boilers are much smaller and more compact for purposes of economy, meaning that they hold less water and therefore need to react much quicker, more efficiently, and safer whenever there's a demand for steam. Too little water in the boiler and there is a risk of absolutely severe catastrophic boiler failure. Too much water again, and we raise the risk of carryover, wet steam, and that will again impart water hammer on the system, more corrosion and more erosion within the system. We can use either magnetic, conductivity or capacitance probe to send a signal to either an on-off or modulating pump or control valve to control this water level. Typically, an on-off pump is cheaper and is simple to install. Modulating system is responsive, much more efficient, and produce a consistently better quality of steam. So therefore, a much better way of operating your boiler. In a boiler, we also have to look at TDS and bottom blowdown. So in addition to chemicals that we add to the feed water, there will also be chemicals and minerals presented in the raw water. These cannot be turned into steam, and over time we will get a higher and higher concentration of chemicals left behind in the boiler that will behave in different ways. Heavier particulates will fall to the bottom of a boiler as sludge, and we need to get rid of it to prevent it from filling the water space and resulting in a thermal failure of the boiler. We do this by opening a valve underneath the boiler where the pressure inside the boiler will discharge this particulate to waste. We call this bottom blowdown, and this can be done once per day, either manually or by automated time process. Remember, this blowdown is pressurized hot water that will exist at temperatures in excess of 100 degrees Celsius, so needs to be able to vent away any flash steam to atmosphere and be able to cool down, usually over a number of hours until it can then be displaced to town effluents at temperatures of no greater than 43 degrees Celsius. Having said that as well, it is generally about a 2-inch valve that you will find underneath that boiler, and therefore it's recommended to only have it open for 3 to 5 seconds, as anything longer will most likely just be again a discharge of good treated hot water, which will be a waste. When we have a look at TDS control, we also have a chemicals and minerals that won't settle as a sludge and instead remains in a solution, so referred to as the total dissolved solids, or TDS. As the boiler cycles, these chemicals will become more and more concentrated, and left unchecked can produce a thick layer of foam on the water surface, which brings 3 points into consideration. Inaccurate control of water level, as probes may struggle to differentiate between foam level and the true water level. Also, scaling formation on the boiler surfaces of just 1 millimeter thick can result in an insulation inefficiency of 10% of the fuel cost. And thirdly, foam being drawn out of a boiler and into the header, resulting in wet steam, which will cause low energy system, which will also cause erosion, corrosion, and also the very dangerous water hammer that you will find within a steam system. The TDS can be controlled manually by treating a cooled sample of water with chemicals. And when a high concentration is found, a volume can be bled away from the side of a boiler, as seen here, at which point the level control probes registers this demand for water in the boiler, and the operate volume of hot water is supplied from the feed tank. We can also perform this TDS blowdown automatically by using a conductivity probe ahead of a valve at the same time of a boiler to modulate out a small mass of water whenever it reaches a high concentration. But just to blow this down and just let it go to a pit is a little bit of waste. So as with bottom blowdown, we can't use this anywhere else in the process, and it needs to go to a waste via a blowdown vessel. But as it is not full of heavier particulates, we can recover some of this TDS water blowdown that we are doing. The pressurized hot water is forced to flash off across the flash vessel, and this clean flash steam is taken to the deaerator at the head of a feed tank. That is that section over there. So as your TDS is blown down in your flash vessel, the flash steam that is now clean can be utilized in your feed tank, and the more contaminated water can be recovered through a heat exchanger by means of circulating your feed water and then being discharged down to your drain, which is then being discarded. Also, steam metering. It is always recommended that the mass of steam leaving the boiler house is monitored so we have an understanding of how efficient the boiler is producing steam. This will give us a true picture of our steam consumption in our plant. If the incoming raw water, water leaving the feed tank, and the steam leaving the boiler are all metered, then the steam system can be benchmarked to get an accurate understanding of what the true cost of steam is. Now let's have a look at your steam distribution line. Once steam leaves the boiler house, it enters the distribution system, which is where most of the consultants and contractors will work. However, if a steam is not generated correctly in the boiler house, this can cause a number of issues, ranging from safety to steam quality and energy inefficiency. And therefore, it is important that we take steps to ensure that the steam is both moved at and arrives at the process in the correct condition. So a little bit earlier, we spoke about the volume of steam. And again, pipe sizing is critically important. We look at the pressure versus the volume curve earlier, but this graphic demonstration that if we generate a ton of steam at 2-bar gauge, we would need to distribute it in a 4-inch pipe. But at a 10-bar gauge, we would only need a 2-inch pipe. So there we can see the difference. Again, because of the volume at 2-bar, we know that the volume of steam is 0.603 meters cubed per kilogram. And to accommodate this 1,000 kilograms per hour at 2-bar, we would require a DN100, and that is most likely taken at a 25 meters per second velocity. Doing exactly the same thing, 1,000 kilograms per hour at 10-bar, because we now know that the steam is more compressed to 0.177 meters cubed per kilogram, we can see that we require a much smaller steam main. This is also the reason why we always advise that we pressure reduce the steam as close as possible to the process area in order for us to keep our pipelines as small as possible to distribute at as high as possible than what we can. So this has two benefits. First and foremost, a huge infrastructure cost saving. And secondly, as I've just mentioned, a smaller pipe radius means fewer heat losses from the pipe, which means less condensate to be removed. So sizing pipes, when selecting pipe sizing, we can use one of two methods. Generally, we select by pressure drop and long runs and for distribution mains, which is greater than that of 50 meters. And this is sized by a combination of calculating the steam load, the radiation losses, and the resistance in pipe valves and fittings. So there are quite a few complicated formulas that we utilize for this, and or the chart as you see on this side here. But there are calculators, online calculators that we can utilize. For shorter runs, generally your branch lines, which is smaller, less than 50 meters in length, we generally use the steam velocity method, where we obviously would utilize around about 25 to 30 meters per second at various pressures. You would just come across, have a look at what your requirement is vertically up, and you would find the size of your steam pipe that is required. When consideration for design or for distribution, there's a couple of things that we want to have a look at. So steam is a gas, and we need to observe different methods of good working practice compared to that of liquids. For example, the use of eccentric reducers rather than concentric reducers. What this will enable is the flow of condensate will be much more smoother. We won't cause a restriction or a buildup, and also hitting that concentric reducer will mean that the water will almost like, well, it will ramp sort of, because water don't flow at 25 to 30 meters per second. It wants to flow at 2 to 3 meters per second. So putting that in a system where we have steam flowing at 25 to 30 meters per second, as soon as it hits that piece of a wall, it will again re-evaporate into your steam system and contaminate your steam. Having a look at your low points. So having a look at low points is we want to ensure that we trap any low points in order to get rid of any condensate buildup. Again, here we can see that we want to eliminate this type of effect by means of our steam trap set. So everywhere the pipe has a up or downward direction or end of a line, we would want to install a steam trap to eliminate that. And again, coming back to strainers, on a steam system, we want to install a steam strainer on the side so that we have less water buildup on the strainer, opposed to that of liquid systems where the strainer is installed to the vertically, and therefore ensuring a pocket water that will be collected within the strainer. Also, when we have a look at the design considerations for distribution, when we talk about the main lines, we also want to have a look at the direction of flow, the slope that main line will do, which is 1 meter to 100 meters slope to aid the condensate removal, and also ensuring that the steam takeoff is from the top. So we want to ensure that, so that again, as I showed you the previous slide, we have a condensate film at the bottom, that not to be sucked up into the takeoff, and therefore again create problems within the steam system going to a control valve or maybe a plate heat exchanger. As well, what we would want, steam traps we will install every 30 to 50 meters, and we want to do that with a correct drain pocket, which is seen in this example. So for up to 100 millimeters, we want our drain pocket to be the same as our size, mainline size, and we want to have a pocket depth of approximately 100 millimeters in minimum. Anything above 100 millimeters from 125 to 200, as you can see, D1 needs to be 100. So the minimum of 100 millimeters should be your drain pocket diameter, and the length of that pocket should be a minimum of 150. And anything exceeding 250 millimeters above, we can see that D1 needs to be a half of what your size would be, and your minimum depth is the same as your main. And that will ensure that condensate that runs through this system will fall into the pocket and therefore will be removed from the steam system. Also, when it comes to heat transfer, is the arch enemy of that. And as you can remember, we also spoke about adding the chemicals into the hot well to remove any oxygen and non-condensable gases. But air will also be present because when steam condenses, it pulls a vacuum, and unless we get rid of it appropriately, it will cause us a number of problems. First and foremost, it will become reabsorbed back into the condensate and turn into carbonic acid. This will cause erosion, it will cause corrosion, my apologies, but also means that this carbonic acid is returned to the feed tank. It will need to be treated with much more chemicals. And most likely, you will have more TDS blowdown. And secondly, any film of air at the process will create an insulation effect and result in the actual temperature of the steam being lower than that observed. That will cause process slowdown. This is also Dalton's law of partial pressures that you will notify there. And here we can see barriers to steam or heat transfer, and we can see as we supply steam at 1 bar, we hit this air film and we can see a dramatic drop in temperature going across these films. So once we actually finally get to our product, we can see that we have lost quite a bit of temperature within the system. And as the slide says, 1 millimeter air is same insulation effect across the thermal barrier as 15,000 millimeters of copper. So we want to get rid of air within the system as well as non-condensable gases. It is also important to make sure that processes can be safely isolated. Using a double block and blade principle wherever possible, and as you can see, whenever space constraints or downtime are issues, then these can be addressed by bringing in the third valve required into a standard single valve facing face-to-face. So this basically replaces all of that. So where isolation is of utmost critical importance, we recommend the double block or bleed valve for that application. Again, insulation, in good condition, and it must be secured, absolutely. We just saw a little bit earlier that 10 bar gauge have 185 degrees Celsius. Having pipes that are uninsulated or valves that are exposed to this temperatures, it becomes a safety aspect where people walk past it or have to handle it, and without the correct PPE can easily burn. But not just that. When you have a look at uninsulated pipes, these are generally the cancer of a steam system because of the heat emissions that you will see within it. So you cannot see the loss, but you get the condensation through the heat emissions, and therefore you will create so much more water within a steam system. But also, if we are moving hot steam in a much cooler steam pipe, then we are inevitably going to see much more steam losses as it's heat to the pipe and produce condensate, which means not only in distribution inefficiency, but also more steam traps required and a greater risk of erosion, corrosion, and water hammer. And there we can see if you have a proper insulator system, we can reduce that heat losses up to 90% of it. Staying within the pipelines, we know that when you add heat and subtract heat, you are going to get pipe expansions. And while Spirax don't make expansion devices anymore, we can offer you guidance of how much expansion you can expect to see if we know a few key parameters such as your temperature, surrounding temperature, your pipeline pressure, which relates to temperature again, your pipe size, as well as the length. We can easily work out what that expansion is within that system. But just putting in pipe expansion is not enough. You really need to make sure that you have pipework support. So as far as support centers are concerned, steam is a gas and therefore the infrastructure is much lighter in weight than that of liquid system. So we need fewer support centers, but we don't want to have too few or we risk the pipework sagging, which again can result in the problem of too much erosion, corrosion, and again, water hammer. So again, we need to make sure that we do this correct. I think I look at the process application, so you can see that it is important to ensure that the steam arrives at the process in the best possible condition, at the right pressure and at the right temperature and at the right volume. Processes where steam is used can vary from air handling units, plate heat exchangers, sterilizers, pasteurizers, and jacketed vessels, just to name a few. So steam at point of use is required at the right pressure and temperature, as I've just rightfully said. So in order for steam to be effective, to give up its heat energy, we should ensure that it arrives at the process at a suitable condition. So typically what this would mean is that it should be at the standard of BSEN 285, which means that it needs to be dry, so we know the energy content, not contaminating the process we used for direct injection. When steam is almost close to 100% dry, we can utilize the energy value of the evaporation rate. It should be free of air, so we know the temperature. And again, this comes back to Dalton's law of partial pressure, where air could subsequently show a lower temperature than that of what the steam tables will show you. Temperature and pressure, so that the process can take place safely and efficiently. And lastly, absolutely free of rust or particles, so there's no process contamination. One of the first things we do in order to condition the steam is to keep it as dry as possible by removing the entrained moisture that makes it wet. This wetness results in erosion of sensitive areas such as your flow meters and also your valve seats when moving at a fast velocity across them, but also drags the energy of a steam down once we have contaminated steam. By passing wet steam across a separator, the steam condenses on the baffles and the condensate is then removed across a steam trap, leaving the dry steam to pass towards the process where it is now rich with energy and less likely to cause erosion. Also, as what we said with a strainer, this is now correctly located on its side, so therefore it is used to remove any particles and not allowed any condensate buildup that is within the system, as well as then drying, passing it through the pressure reducing valve. This will aid in the reduction of pressure and also improve the quality of your steam. So generate and distribute at high pressures means that we will have smaller pipes, which equals a lower cost of piping, your fittings, your lagging, the installation, and also it will have a much smaller surface area, therefore less reduction in heat losses. We also now just recently said that reducing the pressure at a point will give us much drier steam. Again, is why we want to reduce closer to the process medium than much further back. Boilers are much more efficient when operating at higher pressures. And then I think the most important point is this one, is that a boiler operated at high pressures has a greater thermal storage capacity and is much more able to cope with fluctuating loads. Also, when we condense steam at process at low pressures, we know that we have a higher enthalpy of evaporation, which is much more efficiency of our heat transfer. Less heat remaining in the condensate means that we will have less steam, flash steam formed, and therefore we have greater efficiencies within the process. Protection of capital equipment from overpressing, absolutely. So therefore most of our apparatus that we utilize are much lower than that of which the boiler is producing the steam, and therefore we also ensure optimum flow from a pressure drop from a high to a low pressure drop. And we basically make use of a pressure reducing station to ensure that we have the right pressure and temperature at the point of use, as well as the right quality of steam. Within this pressure and temperature or pressure reducing station, we have two units, which is our PRV, our pressure reducing valve, as well as our safety valve. So a process will have this PRV to ensure that any overpressure won't result in any failure, and also because steam gives up its energy much easier at a lower pressure. The safety valves we know is required to protect both life and processes in the event of a control valve failure and or a pressure reducing valve failure, and should be correctly sized and installed. So once we have a look at safety valves, one particular point of safety valve is the design, installation, and also the commission engineer should also observe is to allow for the correct installation of any safety reliever. First and foremost, we can see that we have a falling pipework. Away from a valve allows for any steam passing the seats, which will quickly condense in the pipe to drain to a low point where it can be taken to waste. And that is that guy over there. The run of discharge should be kept as short as possible and without a cowl or a hood. This is to prevent any unnecessary and unexpected back pressures, as this will greatly reduce the discharge capacity of the valve if you have a hood over this section of discharge. And ladies and gentlemen, I've seen this so many times when we walk on sites where these valves aren't piped to normal head height or face. You know, when you look right or left, you're almost immediately looking into that pipe. You have to pipe this to a very safe position so that we don't endanger any lives. And then lastly, the pipework must be supported by means of a bracket, because as soon as this valve opens, because of this violent action that you will find because of a change in state or a change in volume, because of a high-low pressure, you are going to have a very violent action over here, and you need to support that pipework as well. All right, having a look at control valves. So control valves add a greater degree of accuracy, as we know, in control, and it can also be either pneumatic or electrical. So here we can see that you have the option of 1 or 2, which is on-off or modulating control valves. It's generally a 2-port valve that is required for steam, no 3-port valves as opposed to water systems. And we need to select and size this valve correctly. Sizing the valve correctly means that I would require the upstream and the downstream pressure, as well as the volume required to pass through this control valve. Many a times people install this valve line size, which means that this valve will be grossly oversized if you have a very big pressure drop. The larger the pressure drop over a control valve, the smaller you can have at control valve. Generally, Spirax-Sarco, we size our valves on critical pressure drop in order for that valve to be as small as possible and most cost effective, as well as to ensure that the valve is operated as far away from the seat to ensure that we do not wire draw the control valve. Control valves also make use of 3 different characteristics. So first characteristic is your fast opening. Second characteristic is your linear, and the third one in a control valve that's Spirax-Sarco cell is the equal percentage. Fast opening valves are generally for applications such as your boiler feed water valves. These are valves that you want to open as soon as it opens very slowly. Here we can see a valve that is 25% open will almost give you 80% flow. A linear valve are generally for filling or controlling. So you want to know that if that valve is 50% open, you will have approximately 50% flow. And as I've mentioned, the standard trim or characteristic that Spirax-Sarco uses in its control valves are the equal percentage. And here we can see where a valve is operating at 50%, you are most likely getting something like 20-25% of a flow. Meaning that if I control as far away as possible from the seat, I will have less wear and tear on it, and therefore also allows me to give a little bit of greater control over that control valve. When we have a look at steam metering, and just as it is important to meter the steam leaving the boiler house, as what we said a little bit earlier, it is also recommended that each individual process has its own dedicated meter, and that is for 3 reasons. My apologies. The process of equality, first and foremost, to control. Secondly, is to process efficiency and fault finding. And thirdly, it is for custody and budgetary requirements. The nice thing about the steam flow meter is that it records everything every minute. If you have a trend line on it, it can show you what happens. And as soon as you start utilizing more steam within a section, it can show you either the inefficiency of that system or it can show you a problem where you might have a failed open steam trap that is now requiring much more steam than what the process is usually requiring. And therefore, it is also a matter of finding fault within that system. But installing the steam flow meter requires a couple of things. It's just not a meter that I would put in a steam system and just hope that it will last. We have to ensure that we produce this steam flow meter with dry quality steam. And as we said a little bit earlier, the way we would want to do that is by means of a separator. Separator again will eliminate any entrained moisture within your steam system or with any carryover from a boiler, and therefore protect your isolating valve as well as your flow metering system, ensuring good quality steam and therefore also ensuring accurate metering. When having a look at grades of steam, we already mentioned that certain processes will require steam for direct injection purposes. And this means that we simply cannot live with the risk of any carryover of boiler water, any wet steam, or particulate into a process that may consider as being sterile. The steam conditioning triangle shows us they expect that processes will demand that steam is generated in a dedicated steam-to-steam generator using an excellent quality of chemical-free water and then distributed to the process in a stainless steel infrastructure to safeguard its integrity. So what we can see from this pyramid is first and foremost, we have our plant steam. Plant steam generated in a normal economical industrial boiler. And yes, there are their processes, but this is generally for steam that does not come into any contact with any product. Here we have some industries, HVAC, laundries, pulp and paper, petrochemical. In some food and bev plants, you would also find this. A much more improved steam is the one that is filtered, and this means that that has a clean steam filter within that system, and it is used in food and beverage plants, but it's the better or more improved steam than that of plant steam. Still not preferred, but if steam does come into contact with consumables, we would rather want to go for clean steam. Clean steam, as I've just mentioned, is steam that is manufactured from a steam-to-steam generator, and that is something that looks like this, a clean steam generator. These are generally used in your hospitals, your cosmetic, food and beverages, where steam becomes an ingredient of your product. And then pure steam, which is the ultimate grade of steam, is utilized in your pharmaceutical and your biotechnology. And again, that will be produced through a pure steam generator. So again, once steam becomes an ingredient of your process, then we need to start moving to clean steam. Where it is not, yes, steam is sterile, absolutely. It is clean when it's produced. But in most cases, if I had to come to your side and ask you to drink your condensate, you will most likely tell me that I'm mad. Yes, it is because that is not clean. It is sterile. Yes, it has been produced in a boiler, But when it comes to consuming or consumers, therefore, as soon as it becomes an ingredient, the steam grade changes dramatically. Right, so our easy heat steam hot water plate heat exchanger. A common process is that the use of a plate heat exchanger to generate hot water for either domestic and or for heating of process purposes. And this works very efficiently when compared to traditional heat exchangers, as it generates hot water from steam on demand, reducing the need for any storage vessel, which in turn reduces your footprint space, the running cost, as well as PED inspection costs. So the Spirax Soccer Easy Heat steam system is an instantaneous hot water system that controls your temperature, your water temperature within 2 to 5 degrees Celsius. If you require up to 1 degree variance, then it does become a little bit more complicated, but it definitely can be done. What this easy heat system does, as I rightly said, is it takes away the need for a storage vessel and therefore the associated problems with that. So we know that when steam gives up its heat energy, it condenses. In other words, it changes from a state from gas with a larger volume to a liquid that has got a much smaller volume. And this condensate will exist in two areas of a network. First and foremost, when the heat is given up in energy to the pipework leading to your apparatuses, it means that we will see a roughly 2% of a mass of steam that's being generated that will condense. And we know that the second place where we will definitely find condensation is at the process itself, which is where we want the steam to give up its total energy. So, if we can recall from a steam table, we know that boiling water of 100 degrees Celsius at atmospheric pressure can contain 419 kilojoules of energy. So when steam condenses, it gives up all of the energy that we add to the boiling water, which was at 2,257 kilojoules per kilogram, and no more. This means that the condensate that remains after the steam has given up the latent energy, which is the 2,257 kilojoules, is still valuable to us, and we can use this if we can return it to the feed tank. So it's very important for us to recover condensate, because recovering condensate excuse me, means that we have hot water getting back to our feed tank, which is treated water with a high heat content. And as I showed you guys earlier, every 6 degrees we can raise our feed water temperature by means of condensate return or flash recovery or any other heat medium recovered. We can save 1% of our fuel bill. So what does a condensate pipe carry? You know, when steam is under pressure, so is the condensate. So referring to the process above, or the process you see here, steam at 7 bar gauge will have a temperature of 165 degrees Celsius. But so too will this condensate, because the same pressure you will see here at 7 bar, you will also see prior to the steam trap. So if a condensate then passes across a steam trap and falls to a pressure of 0 bar gauge, atmospheric pressure, we now know that it can only contain the 419 kilojoules. Although, before the steam trap, we now know that that 7 bar gauge, we have an HF of 721 kilojoules. So the only way that this 302 kilojoules, the 721 minus the 419, excess energy can be really released is by producing flash steam. But remember, steam has a volume that is 1,650 times greater than that of condensate, which is now your liquid. And the image down in the left corner, this one over here, guys, we can now see that this demonstrates not only important that the size of a steam pipe is correct, but that we also need to consider that the condensate is a biphase whenever we see a pressure drop across. So what this pipe is going to have to handle is not just the condensate, but also the flash steam within it. And as you can rightfully see here, even though the flash steam of 13 kilograms of mass is the smaller amount of 87, we can see that the volume is the greatest, which is the 99.6. So this condensate pipe, if undersized or just sized for the liquid system, will be undersized and it will cause problems within the system. So once the condensate leaves the process, we need to get rid of it, as we can use it for the heat exchange so that we use a steam trap, which is basically a non-return valve that traps in a valuable energy in the steam, but allows the liquid condensate to escape. There are a number of traps types that are different to operation principles, but all need to be sized and selected in accordance with whatever that process, application, or conditions are. There are three operating principles in steam traps that we have. First and foremost is the mechanical type, the thermostatic, and also the thermodynamic. And each of them have their own place within a steam system. So sizing of condensate lines upstream and downstream of a steam trap. So when we size a condensate pipe between the process, we must consider both of those conditions, as we've rightfully said that the steam or the condensate prior to the steam trap will be under pressure and at a much higher volume, energy value. As soon as it moves across the trap, we will now sit with two conditions, which is a flash and a water condition. If this was just a water condition or just a flooded line, then we could easily have used the chart and just utilized the top part of it where we are sizing it just for a liquid system. But because we now know that because of the energies moving across the steam trap, we have an up and a downstream, and with different temperatures, we have to take the flash steam in consideration, which is from this curve over here. So we would require the 7 bar to our 0 bar where it will flash off. So it's 7 bar prior to the steam trap, 0 bar after the steam trap. And from this saturation curve, we will then move vertically up to our load that we would have. And in this instance, it was 100 kilograms per hour. And where we would now cross those two lines, we would utilize the same or follow the same lines. And therefore, we can now require a 25 millimeter line. That is how we would size that condensate steam line. Many a times, contractors and installation contractors and consultants that is very familiar with liquid systems might miss this point of a flash steam and therefore undersize the steam, the condensate return line. So steam trap selection. So we would obviously have a look at the application and the type of a plant that is required. We would need to know whether that system is temperature controlled and if it is a critical control system. What is the condensate removal and return system that's currently in place, as well as what is the steam condensate pressures up and downstream. You have to understand what is that differential pressure. Again, what is the load variation? Is there a startup condition? Is it a running condition? Are there the possibility of freezing now that we're in winter? Some plants definitely have this challenge. Is there a lot of air venting within the system? And also what material and connections are required from the plant. So once we know all this information, we can easily identify or correctly size the steam trap and ensure a correct installation and or sizing. In many cases, we would have a stall condition within a heat exchanger. So as certain processes will only require steam at low temperatures and therefore low pressures, it may mean that the steam pressure is unable to overcome the back pressure placed on the downstream of a steam trap. This means that when there is a low demand for heat by the process, the steam pressure will fall and the condensate backs up into the steam space. When this happens, the condensate will not move past the trap and heat will not enter the process, which is what we refer to as a stall condition within this section. An automatic pump trap can overcome this issue. It basically works as a standard steam trap whenever there is a differential pressure. But as soon as stall occurs, a biphase switch calls for an input of high pressure steam from the head of a control valve, which is capable of pressurizing the condensate to overcome that back pressure. So as soon as this switch inside realize that it's in stall condition, a rush of steam will come in from our motive pressure and the steam trap will then become a pump, which will therefore then discharge any condensate and overcome the back pressure. However, on calculating the steam charge, we may find that there will never be enough of a differential to overcome the back pressure. And in many cases, the load may be such that we will always need to pump the condensate away. Here we can use one of two types of pumps, such as an electric condensate recovery system. The pros, obviously, of electric recovery system is that we will be able to move a large amount of condensate very quickly, even when the steam boiler is switched off and in a small pipe diameter, which is an advantage. The unfortunate of an electric pump is it requires electrical installation, so therefore energy to move a condensate becomes a problem. We cannot install it in a non-ATEX area, and also, as we have spoken a little bit earlier today, condensate must cool to sub 100 degrees Celsius, otherwise you will find cavitation within the pump if you have not made provision for it. Now you're going to tell me there are pumps that can handle a higher temperatures than 94, 100 degrees Celsius. Yes, there is. And if you put one of those pumps in, that point will not be applicable to you. Right, the second one, as I said, is we could use a mechanical condensate recovery pump. My apologies. We could decide to use this motive energy in the steam that we already have on site to shunt the condensate back. And the pros in this instance is that you have no electric installation, so therefore you don't have that additional cost. It is ATEX safe. It uses no electric energy. It uses a plant steam, which is already available, and it can recover energies that of exceeding 100 degrees Celsius because that will not cavitate. Obviously, the negatives are that you can only move a very small quantity of condensate compared to that of electric pumps, and you can only operate when the motor steam is available. So therefore, if the boiler is shut down, this pump will unfortunately not operate. So the flashed curve shows the effect of high temperature, high pressure condensate undergoing a pressure drop, as what we spoke a little bit earlier. And if we know the pressure upstream of the trap and downstream, then we can calculate what quantity of flash steam will be generated and therefore know what we can recover. An example of flash steam recovery shows the high pressure temperature condensate fall in a pressure temperature inside a flash vessel, at which the point of resulting flash steam can now be diverted to another process like a preheater in a air handling unit, as what we see over here. And the result of condensate as a low pressure temperature can then also enter the condensate recovery unit and therefore be recovered back to the feed tank. So any flash that comes from a higher pressure, we can utilize a certain amount of that where it would have gone to waste if it was just supplied to the condensate recovery unit by normal means. My apologies for the values in pounds, but here we can see that the flash recovering saving in this vent condenser is in this instance was 14,573 pounds, which equate to 48 kilowatt. We also had a reduction in water cost by recovering the water back to the feed tank, and as well as the saving from the increased feed water temperature that the condensate had. All of that together was a 44 kilowatt saving, and in total in this example, they saved 40,038 pounds within that recovery system. So it's just imperative that we recover any condensate that might be either discharged to ground, and even so, most of or sometimes what customers come and tell me is that the condensate is contaminated. We don't want to take the chance to recover it. There are turbidity monitoring systems and or contamination systems out there that we can install to detect these contaminations and to divert the condensate, from which we can then recover the energy within that condensate and then dump the condensate rather than just dumping it completely. So we need to recover that back to the feed tank. So in summary, steam is a highly efficient and effective heat transfer medium which can be utilized in most of a plant. And we need to do that effectively and efficiently. Steam is very easy to distribute and to control by means of a two-port control valves, as well as by controlling either the pressure and or the temperature. Steam is safe and efficient. Efficient boiler house and distribution practice are key, as what we said, with the right pressure, temperature, and volume. We have to consider and evaluate our oxygen reduction and energy recovery options, as we have now rightfully seen that by recovering energy, we can save a lot of money, not just water, but also the energy within the condensate. A good steam condition is fundamental to affect any heat transfer in the air handling units, the plate heat exchanger, or any heat transfer application medium. The effective condensate management and removal of it will promote system health and absolutely provide energy saving. By not having an effective condensate management system, we are going to have product spoilage by means of not getting rid of condensate and or having store conditions, which again will prolong the process, which will again cause product spoilage. As what I said, the store condition. And then monitoring overall system efficiency for boiler effectiveness is key to identify any prioritizing areas for improvement. So to measure is to know, and if you know, you can put it into values and you can actually then do something for that. So ladies and gentlemen, thank you very much for your time and your attendance. I really appreciate it. That brings us to the end of our slide. Debbie, I don't know if there's any questions that we can maybe field. I see that we're sort of on the time. If there's not any, if we can't answer any questions at this point of stage, we will definitely get back to you guys via mail and or by means of contacting you to answer any of those questions.
Hi, Andre. I just would like to just raise a few questions, since there was 4 questions that came in, certain parts, especially in the beginning of your presentation. The first one was regarding the TDS control in boiler house. The question is, in the absence of a TDS meter or TDS control, can online conductivity be used?
So if there is no TDS control measurement, what's going to happen is, yes, you will physically have to take the sample, identify what the TDS value is, and from there do either bottom blowdown to control the TDS. So the TDS measurement that I showed you in the presentation means that it is a continuous measuring monitoring system, and therefore will automatically open and close as the values, as the set point is either reached or not reached. So yes, you can do it. It's just going to mean that it's going to be a little bit more cumbersome and a little bit more manual labor. The problem with manual labor is that if it's not done regular basis, you do run the risk of allowing the TDS to run away and therefore cause the foaming and the carrying over and or scaling, which is problematic for your boiler. I hope that answered your question.
Okay, thank you, Andre. And then the next question is regarding the steam distribution line. How many degrees of superheat should the steam leave the boiler house at prior to reach the process points?
Great stuff. Thank you very much for the question, for the lady or gentleman that posed that. In normal economical boilers or industrial boilers, superheat cannot be generated in a normal boiler, although if it does have a capability of doing it, my advice would be that for distribution purposes, superheated steam can be utilized. We generally don't advise on how much degree superheated steam, as superheated steam, when utilized for heat transfer, is of less importance. If you do generate it in superheated steam and you use it for distribution purposes, you will obviously need to desuperheat it at some point to get to the saturation enthalpies, and therefore it becomes a much more complex system. But unfortunately, I don't have an answer for you to say that you would need 10 or 20 or 30 degrees superheat for 100 or 200 meters. In general, if you do produce steam in a normal economical boiler as saturated steam, by installing a boiler house separator, you will definitely discharge or eliminate any of a carryover and or water moisture you will find within the steam leaving the boiler house, and therefore have very close to 100% dry saturated steam after the boiler house separator. And once your insulation is very good all the way from the rest of the distribution system, and you have the advisable amount of steam trap pockets within the line, you should be fairly very good quality of steam at the end of a process. But if your process does call for the superheated steam, yeah, I think that is something you would want to take up with that boiler manufacturer. So I apologize for not being able to give you the direct answer you would require on that.
Okay, then I think we still have time for 2 more questions. This one is regarding correct safety valve installation. The question is, can you advise an installation of a safety valve that is installed inside a building?
Yeah, so generally when a safety valve is installed inside a building, you would always want the pipework to go to a safe place. So that means that it would either be down to a drain and or generally up through the roof onto the outside. You must remember a safety valve, as I said, is something that is protecting something, and as soon as that relieves the pressure, it means you have a condition in a pipework or an unsatisfactory condition which needs to be attended to. So getting rid of the steam and at that volume, my recommendation would be to see if you can take it outside by installing the correct pipework. If not, then in its own dedicated line out, either through a drain somewhere, again, safe. There's no demister and or buffer that you can put on the end to dissipate the energy. So you'll have to get rid of it somewhere on a safe measure outside either the building or into a drain somewhere where it won't cause any damages to either person and or to the building.
Okay, and just the last question, an interesting one regarding flash steam. In a system only designed to recover condensate, for example, a system with a mechanical condensate pump, what happens to the flash steam? Is the energy just wasted?
Okay, great question. Thank you very much for that. So the mechanical fluid or condensate recovery system that I showed you guys, you would see that it actually has a vented receiver. I'm just quickly going to revert back to my picture, if I may. So there we can see that this is, you should be able to see my screen in about a second. Maybe you see it?
No, you just have to share it again.
My apologies. Let me quickly share again. Didn't share. Can you believe it? Okay, so you should see now, yes?
It should come through, yes.
Yeah, so what you will see is in this mechanical condensate recovery, your condensate comes into the receiver, as we can see there. And into this receiver, what you do now not see, which, there it is, sorry, my apologies, there's the vent. So what you will find is that that flash steam will now exit the vent and allowing that this is not a pressurized unit. So therefore, that flash steam now rightfully, as you said, does just go to atmosphere and it basically is just being lost. However, we can recover it by means of this guy over here. Just see if I can. So here we have what we call an exhaust vapor condenser, which is we install it on our condensate recovery systems, and there we have now water running through or any other secondary medium of heating. So as we now enter this condensate where the flash would have gone to normal atmospheric pressure to venting, we now run it through it's almost like a shell and tube heat exchanger. We run it through that, we run the secondary water through it, recovering that energy, and we reduce that loss of flash steam to atmosphere. And that is how we recover the flash steam from a mechanical condensate recovery pump. Great question. Thank you.
Okay, yeah, thank you, Andre. It seems that that's all the questions that we have time for now. Thanks again to everyone, all the participants, and for your questions. As we mentioned, you will receive an email after the session with the recording. If you click on the recording, you will go to our training website where you can actually have you can choose from the few webinars that we've already done, as well as this one. And also, if you would, I'm encouraging you to please complete the survey that you'll receive with the next email, and look out for our invitation for our webinars in August. So thank you very much, and thank you, Andre.
Guys, thank you very much.
Everyone have a good day.
Have a great day. Cheers, eh?
Thank you.
Bye.
Cheers.